Good evening, everybody. It's a great pleasure to have you back with us again tonight. Second month we're doing it in person, even though it's a small crowd here. We are also live streaming this. Hopefully that will all work, and the people online can also hear us. So welcome to everybody also online. If you want to give us a shout in the YouTube comments, you're welcome to introduce yourselves and say where you're from, to make this a more global celebration than just those of us here in Leiden tonight. So probably many of you here already know. It's a short introduction to Astronomy on Tap. It's been going since 2013, started in big New York City back in 2013, like you said. But since then it expanded to many other places, particularly in the US, but now also through the rest of the world. And Leiden was the first one in Europe, and we started back in 2017. We're online. Those of you here are here, great, but we're also online, Facebook, Twitter, Instagram, and classical old email if you want to get in touch with us. Those of you here in the room, a few notes. We're all familiar with this by now, but just a few rules. The bar is pin only. I think you might already have discovered that. Please try and keep to the 1.5 meter distance, unless you came together in a small, less than 2 household. Less than 2, that would be 1. Yeah, 2 or less. Try to avoid bunching up too much together, and when you leave, don't all rush out at the same time. But that said, we're really glad to have you here, and it's already great that you're sitting pretty much apart. So that's great. Just a note for those online, you can leave questions for the speakers in the comments box. We will probably by preference take questions from the people in the room, simply because that's easier. But if we have no questions, we'll also go to YouTube. So very briefly, we always do a little bit on astronomy news, and this might have been hard to miss. It sounds like a light item tonight, but just recently there was a paper published in the journal Nature that created a lot of attention. Aliens on Venus, maybe not, but they did find this really cool, this evidence of this really cool molecule. It's chemistry to me, phosphine on Venus. And it's possible that this is connected to life. They did investigate another number of reasons. Maybe it comes from lightning, but you need a heck of a lot of lightning to make this phosphine on Venus. Maybe it comes up from underground, not from glasses falling over. Maybe it comes from volcanoes, but we know there are not that many volcanoes that produce it. And one of the mechanisms on Earth, at least, is life producing this. Or you need very, very extreme environments or chemistry that we don't yet know to be happening on Venus. And that's also quite a strong possibility. Whoops, that was last month's news. Tonight's program, we have the first talk about exoplanets by Matt Kenworthy. Then we have our quizzes. Those online can also participate in the quiz. We'll have a Google form for you. Those in the room have pieces of paper. Just fill them out. We ask you to do this. We usually play in groups, but we ask you to do this on your own or in twos. Then we'll have a short break. Then we have a talk on a completely different topic, but very also exciting astronomy by Sebastiaan Zoutendijk of dark matter and small galaxies. Then we have the quiz answers, the winners, yay, exciting, we've got cool prizes for you. And we just end off by giving the speakers their wonderful beer glasses. So just one thing, I'm going to introduce the 2 speakers, and then we'll go to the first speaker. This just makes it easier in terms of changing over too many slides, because we're sharing the screen with the world. So our first speaker is the gentleman on the left, not the one on the right. You may wonder what the connection between these two are, but Matt spent a lot of time in Cambridge, and apparently his foot once got caught under the wheelchair of a certain very famous gentleman. Didn't break any toes?
No. Still walking.
But in terms of astrophysics, Matt has spent decades working on looking at planets around other stars. Along the way, he's discovered comets around other stars and then also giant gamma ring systems. But he'll be talking about how you find single planets or how you image planets around other stars. Our second speaker, Bas, is now the gentleman on the right, not the one on the left, although he has aspirations to do this. He already plays classical guitar and is learning to play flamenco. But Bas is a PhD student here at Leiden. He works on understanding fundamental physics, fundamental properties of the universe, mostly by observations using telescopes. Currently, he's working on looking at dark matter, and he'll talk about dark matter in smallest galaxies. So, without too much hassle, I hope I too will switch over to Matt's talk, and then we'll get started.
Okay, thank you very much, Wendy, for the introduction, and it's lovely to see you all here at a socially acceptable distance, even better. So this evening, I'm going to talk about a discovery made by a graduate student who's working with me, Alex Bohm, but I thought it was just such a lovely story, it would be great to share it with all of you tonight. So I'm going to be telling you how we take actual photographs of planets orbiting around the nearest stars in our galaxy. I have a picture here. This is real data with an interpolation between the adjacent years. This is the HR 8799 system, with not one but 4 gas giant planets orbiting around it. And this data has been taken over several, almost a decade. So the way we understand how planets are made and stars are made is that we start with large cold clouds of very thin gas dispersed with dust. And gravity comes along and starts collapsing these clouds together. And during the process of manufacturing the star at the center of this collapsing cloud, the remaining dust and gas tends to collapse and form a disk, a circumstellar disk, which starts rotating around the star, and the planets form within it. And so what we have here is a picture from the Hubble Space Telescope, and what you see is a distant screen of ionized gas, which is glowing with the lovely colors. And in the foreground, you can see these little proto-planetary systems. So you see the star is just about to switch on in a couple of the cores, and you see these things in silhouette against the distant background screen of light. So before 1995, this was our picture of how planets are made around the sun and around other stars. So you have the small rocky planets fairly close to the central star. You have the big fat gas giant planets where most of the mass in the solar system in the planets is stored. And then you have the smaller and more distant ice giants further beyond. But the bulk of the mass is between 5 to 10 times the distance away of the Earth from the sun. So big planets made a long way out. So of course, naturally, we said all other planetary systems must look like this. And so this is the picture we had in our mind. Well, it turns out that the first planets that were detected were not detected directly, but indirectly. So when a planet and a star orbit each other, the planet draws a big circle, which is its orbit around the star, but also the star itself draws a much, much smaller circle. They orbit around their mutual center of mass. And so, although you cannot see the planet, what you can see is the effect that the planet has on its parent star. And you can measure the wobble of the star. As the planet goes around once every orbit, the star will draw a much smaller circle. And by studying what we know as the spectrum, we can take the light of the star, split it up into its component colors, and we see these characteristic dark lines, these fingerprints of chemicals in the atmosphere of the star. And we can watch those chemical fingerprints move backwards and forwards one orbital period. So the first planet discovered around a solar type star was 51 Pegasus b. We named the planets, so the star is A. Subsequent planets you discover are B, C, D, E, and F. Very unimaginative, I know. But what really surprised us when this discovery was made was that, first of all, there's a big fat planet, one Jupiter mass, about 1 Jupiter mass, it was around a solar type star. But Jupiter takes 12 years to do one lap around the sun. This planet took 4.5 days. So it's sitting right next to the star, and we have many good ideas as to how the planet must have been made far out and migrated in to be so close to its parent star. But Mayer and Kellogg's published this observation in 1995, and last year they got the Nobel Prize for it. So who says astronomy doesn't pay ultimately? Anyway, so we started discovering that planets, which are in planetary systems completely unlike our solar system. So once they discovered the first systems, many other systems started coming out of the woodwork, just because we realized you can have big fat planets which can make the star wobble a lot, so it's an easy signal to detect. So if we look at all the planets, the orbits of all the other planets around stars are completely random. So if you imagine an orbit is like a hula hoop, and you take a big bunch of hula hoops, run outside, throw them up in the air, take a photo, and then quickly run away before the hula hoops crash down on you. In that photo, a few of the hula hoops will be exactly edge on, which means that the planet will move across the disk of the star. And this led to the second method of how we detect lots and lots of exoplanets. So it's called the transit method. So this is when the orbit of the planet causes it to move the planet's shadow in front of the stellar disk. Now this is a real transit. It's the 2012 transit of Venus. And because the orbit of the Earth and the orbit of Venus aren't quite co-aligned with each other, we only get 2 transits every 100 years or so. And I think you have a very long time to wait for the next transit. But this is a way of detecting exoplanets. And sure enough, if you take a camera and take photographs of the night sky of millions of stars at a time, and take photos again and again and again every minute, every so often you'll see this characteristic little dip. Of course, you can't see the planet itself, it's far too tiny. But what you do see is the effect of the planet moving in front of the star, and you get a little dip of light. And so this principle was the basis for the Kepler satellite. So the Kepler satellite was launched almost a decade ago, and this basically has a gigantic CCD cam. So basically take this iPhone, make the chip somewhat bigger, and again, you just took a photo once every 2 minutes and sent the data down to the Earth. And the end result of the mission is that we have over 2,000 detected transiting planetary systems. And all of these systems in this animation are to scale. So the sizes of the orbits, you can see the inner planets here in the solar system, the rocky planets, but basically all the orbits and all relative orbital periods are accurate. And you can see there's a wild diversity. There's multiple planets, and they all have wildly different orbital periods. It's an absolutely spectacular result. Well, the next thing which brings it onto the research I do is I want to take a picture of these planets. I want to actually see photons bounced from the planet towards me. So what I'd like to see is something like this, a picture of Jupiter. Unfortunately, planets and stars are normally a long way away from the Earth. So instead, you don't see the planet as a discrete disk, you see it as one tiny point inside your camera. And the other problem is you have a honking great light source sitting right next to it. You've got a star which is 1 million to 1 billion times brighter than the thing you're trying to take a picture of. And also, they're very close to each other on the sky. If you go out and see the full moon, the typical separation between the star and the planet from the nearest stars is about 1/3000th or 1/2000th of the diameter of the full moon. So it's a super tiny distance, and you've got a honking great light source next to you. So that's the challenge for doing direct imaging. So when we try and take a picture with a telescope of these 2 dots of light, you don't see a tiny dot. You see this kind of mess. You see this kind of weird bullseye ring effect. So what this is an effect called diffraction. Light comes in particles, but it also can be treated as a series of waves rolling onto the shore. And instead of getting a nice point image of your star and a point image of your planet, you get this kind of weird bullseye effect. And so if you're trying to find a planet somewhere next to a star, these diffraction rings, these circular rings, are many hundreds of times brighter than the planet light we're trying to find. And that's the fundamental challenge which me and my research group have been hacking away at for well over a decade. This turns out to be the big challenge. That effect, one way of making those rings smaller is using a bigger and bigger telescope. The bigger the telescope you build, the smaller those rings become, and the distance between the star and the planet's the same, but the ring pattern gets smaller. So one of the telescopes I used was the Large Binocular Telescope. This is in Arizona, in the southwest of America, and I worked there for several years. Just to give an idea of the scale of this telescope, it's very hard to understand. These small tubes here are ventilation tubes. You have to cool down the telescope in the evening to make sure the temperature is the same as the outside air. I stood in one of those tubes and I can just about scrape it with my finger if I stand on my tippy toes. These are full-grown pine trees next to the telescope. It is a huge telescope, and this is what it looks like when they open the dome in the evening. You can see the two 8.4 meter diameter mirrors there getting ready for observations in the sunset. So, I've told you about these horrible diffraction rings. The first thing we did was to say, well, hold on a minute, let's point the telescope somewhere else, take a picture of another star, and subtract one image off the other. You get rid of the rings, and the planet light should shine through. This is what you actually get if you do that. You get this horrible, kludgy cloud of what we call speckles. And what's happened is that in the time you've moved the telescope from one star to the other star, the optics have bent a tiny bit, typically a few tens of nanometers or so. But that's enough to make the brightness of those rings change a little bit. And because we're looking for such a tiny signal next to the brightness of the stars, this completely messes us up. It's a complete headache, very difficult to do. So when I started doing exoplanets, it was around 2004, 2005. By 2009, we had found no directly imaged exoplanets. And if you're a radial velocity person or a transit person, you were laughing with clover. You were going, yeah, fantastic. So I must admit, I had a tiny feeling that maybe I picked the wrong area of astronomy to go into. Then 2009 came along. And one of the surveys picked up, Gemini Deep Planet survey, picked up the HR8799 system, so it's Christian Malwa and his collaborators. And of course, I've shown you this animation. What's happened is that I've been talking about the transit method and the radial velocity method that find planets in very tiny orbits, days long. The orbits of these planets are hundreds of years. So you can see that we've taken, let's see, it starts at 2016, so this is 7 years worth of data. And you can see none of the planets have done a full orbit. It takes a long time. We're seeing planets much further out than Jupiter and Saturn are in our solar system. How can we see these things? If you calculate the amount of light reflected from the atmosphere of the planet, there's no way we could detect them. And the reason is because these images are infrared images, a wavelength slightly longer than we can see with our human eyes. So what we're seeing is that the planets are glowing. These are very young planets. If the sun is a middle-aged star, about my age, these planets are about 6 weeks old. So they're hot, they're glowing, they're emitting huge amounts of infrared radiation, and we can use the big telescopes with these optics to detect them. And since that discovery, we found 3 or 4 other systems. So there's 51 Eridani b, detected with the G-Bio team, and Beta Pictoris b, which is being discovered with Sphere. And you can see there are 2 very different orbits. 51 Eridani b is a face-on system. But Beta Pictoris b is very close to my heart, is almost exactly edge-on. So we actually caught the first photo on one side of the star. It's in a fairly circular orbit, but because the orbit's edge-on, we can actually see the orbit of the planet pass near the star and then pop out to the other side. So how do we find these planets? So for starters, some stars do actually move in the sky. Now obviously I'm not talking about the rising and setting because we're standing on the rotating Earth, but the stars are flying through the galaxy at tens of kilometers a second. And here's Bernard's star. And this is a series of pictures over 20 years. And you can see with respect to the background stars, Bernard's star is zipping through the galaxy. It's very close to us, about 6 light years away. It's a red dwarf, much lower mass than the sun. And you can see it's just cranking away. And there are a few stars on the sky which do this. So we can actually work out how fast it's moving and how close it is to us. We have to use very large telescopes, I've talked about before. So the other telescope we use for the data I'm showing is from the VLT, the Very Large Telescope. Astronomers are not good with original names. So we're using one of the 8.4 meter telescopes here. And so this is where Alex comes in. Alex and I decided we wanted to try and see how many planets were around stars which way exactly the same as the sun. So we wanted to look at young suns. So we found a group of nearby stars which were the same size as the sun, but what we were hoping was like the sun when it was very, very young with the planets, just 20 million years old. So we got 72 stars. We went off, Alex rather went off to the telescope and took the data. And whilst we were looking through the data, we found some interesting other things. So this is a picture of a circumstellar disk. So I was talking that you form a disk and then the planets start forming within the disk. We found a way to switch off the star in the middle using polarization, and you can see this circumstellar dust. So you can see this dust is reflecting light towards us, and if you wear a pair of polarizing glasses, this is what you can see. You can cancel out the starlight, but the light scattered off the disk is strongly polarized. So we saw this very pretty picture. But back to finding planets. So here's the first photo we took of a particular star system, and this happens to be a binary star system. Now you see all this kind of weird grot hanging around the stars. That's the diffraction pattern and the diffraction rings. This is how they look on this particular telescope. But you can see, absolutely fantastic, the two bright stars. There are hundreds of planets around this star. Fantastic, brilliant. We found tons of planets. The trouble is that it could be just a line of sight effect. In other words, the two stars are very close to us in the galaxy, but we're looking against a distant screen of many, many other different stars. So how do we tell the difference? Well, what we do is we take a picture the next year. We just wait. The star and any planets moving through the galaxy are moving together. They're gravitationally bound, so they move together on the sky. But if we center on the star in the middle of this image, all the background stars jump backwards and forwards. So I'll zoom in a little bit. There's a zoom of 3 stars, and if you look, they all jump in exactly the same direction by the same amount. So all of those are background stars, we can throw them away. But it's key to have 2 pictures. That's how we can tell the difference between the distant background star and a planet moving with the star. So this is where it gets really cool. We did all the first set of pictures, and then we picked 5 of those stars and we said there are these fantastic dim red blobs really close to that star. We think one of those is a planet. And we went up to the telescope and we said, we want another picture of this system. So Alex grabs his laptop and he comes in one day to my office and says, Matt, I've got the data from last night and I've reduced it, so I made it good. I said, oh, fantastic, have we got a planet? And he went, no, none of the things we looked at were a planet. I went, oh, well, never mind, I've been in this business a long time, I don't see planets this often. So these are the 2 images he linked with me. And sure enough, if you look 1, 2, 3, there's a 4th star somewhere out there. They're all jumping backwards and forwards. So never mind, Alex, this happens, it's okay. He says, Matt, no, look again. That's not moving. And I went, whoa, okay, that's pretty cool. That is moving through the galaxy with that star there. And I went, that is pretty incredible. And due to the way the telescope worked, we were able to ask the telescope to change the way they took the pictures, and we actually confirmed the next night, a few nights later, that that was an actual planetary mass planet going through the galaxy. So I thought, that is absolutely amazing, well done. Trouble is, okay, so with that second photo, that was wonderful. And then you can go off to the telescope and say, we want more information about that planet. It's about 14 Jupiter masses, 14 times the size of, 14 times the mass. And so we got a few more images one more time with the telescope. And then Alex comes in again and he says, hey, you'll never guess what. And I said, what is it, Alex? And he goes, there's another object in the system. So this B is already a long way out from its central star. It's 160 astronomical units, about 3 times the distance of Pluto. So who ordered that? Who made a honking great planet far away from a solar-type star? And what we were able to do was we could take pictures at different wavelengths, and we could measure the glow of this second planet. So as I start the animation, which Alex put together, as we go to longer and longer wavelengths, C suddenly starts appearing. That tells us it's a lot cooler, it's a lot smaller, it's a lot less massive. And this is a 6 Jupiter mass planet orbiting around. So we've got a 2-planet system. So I've done direct imaging for well over a decade and got 0. Alex comes along, gets 2 planets in one system. Good for him, it's brilliant. I mean, I'm so happy, it's just such a cool system. Because now we've got a challenge. How do you make honking great planets and get them all the way out into the middle of nowhere? Very, very cool. Anyway, so this is an artist's impression. We haven't taken a picture of it. This is probably what it looks like. It looks like a very dimly glowing coal with clouds and storm systems on it. We see variability in these things. If we take pictures one after another during the night, you can see these things change in brightness. We think they're cloud patterns. We're seeing clouds moving in and out of our field of view. That's very exciting. And of course, this is just showing the scale. There's Pluto's orbit, and this is from the exoplanets.org website, which I thought was very cool. As soon as you get a planet, they run off and make an animation of it for you, which is really cool. You just go to, oh yeah, we did that. Anyway, so they're the two planets, and they're going to take hundreds, many hundreds of years to do one full orbit, but we think we'll actually start seeing their orbital motion in the next 10 years or so. Well, that's all great. What can you do with the planet now we see it? Well, there's one fairly cool trick which I'd like to say, which we'd like to do. So if these planets have a moon system around them, if they've got little moons orbiting around each of these, we can actually, and if the orbit of the moon is edge on to our line of sight, if we're that lucky, and that's an awful lot of luck, but why not? We can do this trick. We can actually see the moon will be darker than the planet, so the moon will make a transit across the surface of the planet. So we can actually measure that little dip and maybe detect an exoplanet. What we definitely will be able to do is see the rotation period of the planet. We'll see the planet and the clouds rotate in and out of our field of view. The next few years, here in Leiden, we're building a camera called Metis, which will go on this, the extremely large telescope. Again, we have no imagination with names. But this is a 40-meter diameter telescope currently being built in Chile, and this will, basically will use the same infrared light and take pictures of the planet. And just to give an idea of the scale of the thing, that's what it would look like in Leiden if we built it in the middle. So if it doesn't work out in Chile, at least we can build it in the middle of Leiden. The clouds won't be great, but yeah, whatever. Anyway, with that, I'd like to say thank you very much, and I'm happy to answer any questions.
Well, thanks, Matt. Could I just ask you to, when somebody asks a question, just to repeat the question so that the people online can hear as well? So yes, questions. I see there's neither one already on there.
Sure, yes.
Thank you, sorry. Thank you for the great.
Is there a limit to the size of the planet? Theoretical limit how big they can get?
Okay, is there a theoretical limit to the size of the planet? So there's kind of a good argument about this. So when is a planet not a planet, and it's when it's a star. So these things are gas giants. They're just made up of a huge amount of hydrogen and helium. If you make them sort of bigger than about 13 to 20 Jupiter masses, they start burning deuterium inside their cores, and so we technically call that a star. But if you could look directly at it, it wouldn't hurt your eyes to look at these things. So it's a kind of very nebulous grey area. You know, there's a range of sizes where you could argue it's like a planet or it's like a star. And how it's actually formed tells you more information. So if it was formed in a circumstellar disk, it's probably a planet. And if it's formed out of an unseparate core of gas which collapsed, it's probably a star. But it's quite fuzzy.
You talked about the wobble. So why does the spectrum you described? What is that wobble?
So why does the spectrum wobble? So it's basically the Doppler shift. So as the light from the star, if you're sitting on the surface of the star, those lines don't move at all. But as the star moves towards us, the waves of light are slightly catching up with each other, which makes the wavelength of the light slightly shorter, so it's blue shifted. And when the star's moving away from us, the waves are stretched out and they're red shifted. So it's the Doppler effect.
So how are you currently limited to, what's the maximum distance of a star system that you can currently investigate? And is there any particular parts of the sky that you can't look at currently?
Okay, so what's the furthest we can see with direct imaging? At the moment, it's about 400 light years. And there's a group of very young stars about 300 light years away from the Earth. So everybody who does direct imaging is looking at the same bunch of stars. So it's a bit of a challenge because everybody has the same phone directory of stars to look at. And it's just a race as to who gets the telescope time and who gets lucky finding the planet first.
Any other questions?
Yeah, maybe it's a bit of a stupid question, but so when you take the images to know if one of the shots is a sun or it's a star or it's a planet, you see moving or not, right?
Yes. So,
in a year.
so roughly a year. If you wait for a year, the way you tell the difference.
Yes, so my question
No, that's a great question. So yes, so the large amount of motion that we see between the two images is the star and the planet moving together across the sky. But you're quite right, the planet is orbiting the star as well. So there's a small amount of orbital motion which is usually added in as well. And we can measure that as well, yes. But we do see it, we totally do see it.
I was wondering if related to the last method you used to detect the planets, is there something that is unique for those planets? So could you also see that in the model, or?
So could we use the common problem, taking the two photos with all the radial velocity planets? And the answer is no, because they're much closer in. They're about 50 times closer to the star. And then that blurring effect, the bullseye target effect, is so strong, we can't get rid of it. So we can't do it. Unfortunately, we wish we could. There are a few nearby stars which would be fantastic to image, but the star and the planet is old. So the planet is like a lump of coal, it's black. We'd never see it. It's really frustrating because there are a couple of beautiful nearby stars, but there's no way we'll see the planet.
Any final questions?
Yeah, I was just wondering, you probably knew already that there were these exoplanets, and by seeing them, how does it help you?
So for the direct imaging ones, we didn't know the planets were there until we took the photo. So that photo which Alex showed is the first time anybody had ever seen that planet, because there's no way you could wait long enough with the radial velocity to pick up that signal. It takes many hundreds of years for the planet to orbit around the star.
Sure, you know these things are there, even though you
Not 20 years ago, 20 years ago, there was an equal argument saying we're unique, there's no other planetary system in the universe, we're special. And this just is complete opposite. Not only are we not unique, there are tons of really weird systems out there, really weird planetary systems. So there's the TRAPPIST-1 system where it's 7 planets tucked within the orbit of Mercury around a red dwarf, completely bonkers. But who made that? That is amazing.
Okay, one last question.
Yeah, sorry, just a curiosity. The image that you showed us for the last star system you found 2 planets for?
Yeah.
That was a binary system, right?
No, so I showed you 2 different sets of images. So just to show the proper motion, I showed you a different star in our survey with lots of background stars, just because you can see all the planets moving. The Tycho system 8998, we're pretty sure it's a singleton. We're pretty sure it's a solo star. There's no other star nearby. It's not binary.
Great, thank you very much. Thank you, Matt, for a very nice talk. For once we get to have an applause, unlike these weird online talks I've been to recently. So we want to say thank you to Matt. And I thought it's really cool, actually. I was going to ask you if you directly image any transiting planets, because they're obviously very different. It's really cool that you imaged Bupic. I didn't know that. So next up, you will be excited. We have Stella to present the games. So the first game is related to the talk you just heard, and it's about the exoplanets. In particular, finding the exoplanets in the following images. And I want to say that we are not very mean. We don't have any foreground or background stars in these pictures. So let's see the observations. So first, how many planets are visible in this image? Have you had enough time to count? Okay, let's move on. Is there a planet in this picture? It's going to be a yes or no. I need to be non-existent in this. Okay, next. Where is the planet? I don't think I need to read this out because it's fairly clear. Is there a planet in this picture? How many planets are visible? Is there a planet in this picture? Everybody done? Everybody done?
Yeah.
Cool. We can rotate through them again later. Let's move on to the second game, which is more related to our second talk today. And thankfully we're doing it before, so you will not maybe know all the answers. But it's about dark matter and how much you know about the dark matter. So let's go into this now. First, why is dark matter called dark? Is it because light cannot escape it? It does not emit light? Or because we don't understand it? Second, what is dark matter not made of? Definitely not made of. A, gas and dust. B, black holes. C, elementary particles. Or D, nothing, it doesn't exist. There is only one answer. Okay. So if a galaxy only consisted of visible, regular matter, then the stars further from the galactic center would orbit slower than the stars that are nearer the galactic center. So stars further from the galactic center, slower. The ones that are in, a bit faster. How would this change if dark matter was also present? A, the orbits of the outer stars would slow down even more. B, the orbits of the outer stars would not be impacted. Or C, the orbits of the outer stars would speed up. All of these then compared to the original scenario. All right, next. Who coined the term dark matter? A, Vera Rubin, B, Albert Einstein, or C, Fritz Zwicky? Right, it seems nice and easy. All right, so I'm going to explain this a bit more, and the options are in the next slide, so bear with me. So what happens here is that this image shows the aftermath of a collision between two galaxy clusters. What you see in red, I will move over a bit. What you see in red is the gas, or most of the ordinary matter, and what you see in blue is the position of dark matter. And the question is, what is going on? What's happening? First, I'm going to give you a hint, and the gas is in the center because when these galaxy clusters collided, the gas actually did collide. It formed this one giant clump. It heated up, and it starts to shine in X-rays, and that's why we see it so clearly in the center. But what happened to the dark matter? A, the dark matter clouds also collided into one single cloud. but the pressure from the X-rays drove the dark matter out again. B, dark matter interacts with other dark matter particles in a repulsive manner, leading to the two dark matter clouds slowing down and never colliding, so they stay on either side of the resulting gas cloud. Or C, dark matter does not interact with itself or other matter very much and was unaffected by the collision, and they plummeted straight through the other cluster. Okay, let's move on. I hope you can hear me, but I will move away again in a minute. So astrophysicists are often like detectives. They look at different kinds of hints and they try to use them all to find this unifying theory that connects all of them. Here you see an astrophysicist or a detective using this pinboard to see how they could figure out these three effects that are often used to prove or disprove astronomical theories. And they try to see if they can prove the existence of dark matter, or to put it differently, to see if dark matter didn't exist, how these effects would change and if they would change. If you are already familiar with these effects of gravitational lensing, cosmic microwave background, and barrier acoustic oscillations, you can go ahead and answer the question. If you, but I will give you a bit of an introduction to all of these so you can maybe give a better answer. So gravitational lensing, shown here in blue, happens when, because of the gravity of very massive objects such as galaxies or clusters of galaxies, and when light rays go near these massive objects, they are bent. The cosmic microwave background shows the density fluctuations in the very, very early universe. So the red points are higher density, slightly higher density, and the blue points are slightly lower density areas. And finally, the baryonic acoustic oscillations are a pattern in the distribution of galaxies at present time. Basically, what I'm saying is that statistically speaking, galaxies prefer to be at a certain distance of other galaxies. And why is that? The answer comes from a very early universe where the matter all wanted to fall into regions of higher density due to gravity. However, there was also radiation. And since regular matter interacts with radiation, radiation prevented the regular matter from falling in and instead pushed it out. Whereas dark matter doesn't interact with light, so it carried on concentrating. So what happened is that dark matter ended up in clumps in center of these, and regular matter ended up as bubbles around this central dark matter clump. And as time went by and these overdensities grew, we see that these are the preferred locations for star formation and therefore preferred locations for galaxies nowadays. So, the question is, how would these effects change if there wouldn't be any dark matter? Do you need more time or shall we go? Okay, cool. According to the standard model, what is the percentage of dark matter of the total content of known universe? Is it A, 5%, B, 27%, or C, 68%? Right? It's a bit of a wordy one. So the dark matter detector Dama, located in Italy, has detected the exact pattern that is expected from hits of dark matter particles. These hits peak in June and they dip in December. But why is there such a seasonal pattern? A. In the northern hemisphere, June sees rising air temperatures. This makes atmosphere more transparent to dark matter particles, so they're easier to detect on the Earth's surface. B. In June, the northern hemisphere is tilted towards the sun. This leads to more dark matter particles hitting the northern hemisphere as they get deflected towards Earth by the gravity of the sun. Or C. In June, the Earth is moving fastest through the dark matter-filled galaxy, and in December, it is moving the slowest. All right. And now, final fun question. If we have a grain of sand for every star in the Milky Way, how much sand would we have? A large sandbox, B, one beach, or C, more than all the beaches on Earth combined? And finally, we have a tiebreaker. How many exoplanets have been discovered to date? Do you need to go through them again? Shall I rotate through again? No need? No need. Okay. You sure? Okay. In that case, we have a 15-minute break, I believe. Then 15-minute break. Okay. Thanks, everybody playing. Okay. Thank you, everybody. I think everybody is expectantly waiting for us to get back. So I have already given an introduction to Bas, but once again, here is Bas. Are you going to play us a micro?
Not today.
No, he's going to be talking about dark matter in smaller galaxies.
Thank you. So I think it's safe to say that dark matter is one of the biggest mysteries in astronomy. It's very important in the evolution of the universe because there's a lot of it in the universe, much more than normal matter, and yet we barely understand it. We only know the most basic things about it. But let me start with the beginning. Let me take you back to the year, if this moves. Yeah. Let me take you back to the year 1933. This was only 80 years after it was proven that there are other galaxies than the Milky Way. And astronomers started to ask the question, how heavy are these galaxies? How much mass do they have? Among them was Fritz Zwicky, who was doing this as the first astronomer. So you can take a guess of how heavy a galaxy is. If you know that this galaxy is 10 billion times as bright as the sun, then it probably has 10 billion stars. And those 10 billion stars are probably 10 billion times as massive as the sun. But if you do the measurement, you find that the galaxy is much heavier than just its stars. There is something else in this galaxy as well, something that doesn't shine. So Fritz Zwicky called it dark matter. And this was quite puzzling because no one had expected to find this dark matter that is maybe 5 or 10 times as massive as the stars in the galaxy. So where does it come from? What is it? It took quite a while to get even the most basic understanding about dark matter. It was only in 1980 that Vera Rubin assembled
observations of a large number of galaxies show that all these galaxies show the same thing. They all have dark matter about 5 times as much as the stars that they have. And this dark matter also behaves differently from the rest of the matter. All the matter that we see in a galaxy is concentrated in a rather small area that forms this usually disk, as you know so well from the images. Dark matter instead forms a large sort of cloud around it that we call a halo. So the fact that dark matter does this and doesn't clump down means that it's something different. It's different from the normal matter that we see here on Earth. And the question is, what is it? That question we have been asking for so long, and we're still asking. We still don't know the answer to this. But there are several theories. I'm not going to go into all of them because there's simply too many. But today I will highlight 2. One theory says that dark matter is some kind of substance that does not react at all. It's completely inert. If you would have dark matter in this room, it would just go straight through us without harming us. The other theory is that dark matter does not interact with normal matter, the matter that we are made of, but it does interact with itself. For example, if you would have 2 particles of dark matter and they would collide, they would go through each other, but they would bounce away. These different theories have different effects on how the universe will look like, so we can test them. The effect they have is visible in the distribution of dark matter in a galaxy, and I'm going to sketch this here. Here I show the distance towards the center of the galaxy with the center on the left. And on the y-axis, I show how much dark matter is at each location. If dark matter is non-interacting, we expect that the dark matter is distributed like this. Far away from the center of the galaxy, there's not much, but as you go closer to the center of the galaxy, it starts to rise very rapidly. Well, for self-interacting dark matter, we see something else. The increase is much slower. It's much less steep. And the difference between the 2 gets larger as you have more self-interaction. So if we can measure the distribution of dark matter in galaxies, we can tell if dark matter has self-interaction and also how much self-interaction it has. But there is a complication. There are also other processes that cause a change like this. When the heaviest stars in a galaxy die, they become supernovae. A supernova is one of the most violent explosions in the universe. And if you have enough of these, those explosions are powerful enough to move dark matter from the center of a galaxy further out. So the density in the center decreases, and the non-interacting dark matter starts to look like self-interacting dark matter. So if we see a slow increase towards the center of a galaxy, how can we tell whether this is because dark matter is self-interacting or because of supernovae? The way to circumvent this is to look at the galaxy with as few supernovae as possible. To get as few supernovae as possible, we have to start with as few stars as possible. So we need to go to a very small galaxy. And such galaxies we call dwarf galaxies. And they may be not as beautiful as those big spirals, but they're very useful. So to measure the mass of a galaxy, we're going to look at one of its stars. The star has an orbit through the galaxy. It experiences gravity from the mass in the galaxy, that's most of its dark matter, and it has a velocity. To stay on its orbit, the velocity and the gravity have to match. If the gravity is stronger because there's more mass, the star has to move faster, otherwise it will be pulled into the center of the galaxy. So by measuring how fast the star moves, we can tell how much gravity there is, and therefore how much mass there is in the galaxy. And if you do that for different stars at different locations in the galaxy, we can say how much mass is at each point in the galaxy, so we get the distribution of the mass. So then the next task is to measure how fast a star is moving. And this is something Matt already touched on in his talk, because we're going to use the Doppler effect. Light is a wave, and as a star emits light, it propagates through space. It's a bit like a ripple in a pond. But at the same time, the star is moving. So as it keeps emitting these light waves, they start from a different location and they keep growing, and you can see where this is going. In the direction of motion, these ripples, which are the light waves, are compressed, and on the other side, they're further apart. And if I'm observing the star and I'm standing here, I see more of these ripples, more light waves coming at me per second. So I see a higher frequency of the light. If I would be standing on the other side, I would see a lower frequency. And the faster the star is moving, the higher the frequency becomes on this side and the lower on that side. And light with a high frequency, we experience as light is bluer. Light with a low frequency, we experience as redder. So by measuring the color of the star, we know how fast it's going. And as I explained before, if we know how fast it's going, we know how much mass there is. So now we have everything that we need to know to do our measurements. And so people have measured the colors of the stars in the dwarf galaxies. And indeed, they found that in the center of these galaxies, the increase of dark matter is just a little bit shallower than we would expect. Because we see this shallowness concentrated in a certain area, we can tell that the self-interaction of dark matter cannot be too strong, because then this decrease will be stronger. So we can rule out strong self-interactions of dark matter. We've narrowed down the possibilities of what dark matter is. But that little decrease in the center, are we sure that it is because of dark matter, or might it still be because of supernovae? Because this galaxy still has quite a number of stars, and some of them will become supernovae, or have become supernovae. So to study this further, we need to go to even smaller galaxies with even less stars. And luckily, this has become possible in the last few years, because as time goes on, we get bigger telescopes and we can see fainter things. So we go to ultra-faint dwarf galaxies. This is a galaxy that I'm currently studying. It's called Iridius 2. This image I made with an instrument called MUSE, which is on the very large telescope that Matt talked about. And you might think, this is a horrible image. The resolution is very low. Well, that's not really an issue here, because the only thing I care about is measuring the colors of those stars. And MUSE is very suited for that, because it can measure very accurately the color of everything it sees at the same time. So just a single image, well, I'll have to make multiple images because this is a very faint galaxy. But we're just pointing the instrument in the direction and letting the light collect. I measure all the colors of these stars. And these colors are much more accurately measured than we could even see with our human eyes. So unfortunately, this picture doesn't even do justice to how well we know these colors and how well we measure the velocities. But going to smaller galaxies also has a downside, because if you have less stars, you can also do less measurements. So the uncertainty on our dark matter profile also becomes larger, and it's getting hard to really tell what is going on here. So to make a conclusion, we need more than a single ultra-faint dwarf galaxy. We need to analyze more of them, which is a task that still lies ahead of us. So we aren't done yet. We still don't know what dark matter is. But if you look at what we've learned since 1933, we already know a lot more than we knew back then. We've ruled out a lot of possible forms of dark matter. We have narrowed down how much self-interaction dark matter has. So step by step, we're getting closer to an answer. And I hope that I've convinced you that going step by step by smaller galaxies, we can contribute to shedding some light on dark matter. Thank you.
Well, thank you very much, Bas. Just a reminder to repeat the questions back
Yes.
for those online. So any questions for Bas?
When you talk about the self-interaction of dark matter, do you mean beyond gravitational negativity? So does that also include interaction with the normal matter that's in the system? How does that work? Many of the direct injection experiments are based on that, so it's easy to see.
Yeah, so the question is, this self-interaction of dark matter, does it also involve interaction with normal matter? Because that is one other way people are trying to detect dark matter. The kind of self-interaction that or the kind of interaction I've been talking about, self-interaction, is only interaction between dark matter. In this theory, there is no interaction with normal matter. But indeed, there are other theories of dark matter, which is called weakly interacting dark matter. And their dark matter is interacting both with dark matter and normal matter. And that you might be able to detect with these experiments that have a very large vat of gas, mostly xenon, and then they hope that there will be a dark matter particle flying through that tank and colliding with an atom somewhere inside, and that gives a signal.
Does that interaction with normal matter also explain how supernovae could affect the outburst of dark matter?
Question is, does the interaction with normal matter explain how supernovae affect the distribution of dark matter? Well, that's actually a different effect. It's not a direct push from the supernova that pushes away the dark matter, because the supernova explosion is mostly light, and in any case, whatever dark matter is, we know it doesn't interact with light. So what the supernova does is it pushes the gas in the galaxy away, and this redistributes the normal matter in the galaxy. And if the effect is large enough, then the normal matter in the galaxy will also pull at the dark matter with gravity, because that interaction they do have. So it will also pull some of the dark matter with it.
Any other questions?
Yeah, so I just wanted, I'm curious about the distribution of the amount of dark matter per galaxy. Does that vary a lot, and do you understand why that is?
So the distribution does have a similar shape in each galaxy in principle.
And the amount.
Oh, the amount, yeah. So there's a trend that larger galaxies with more stars also have more dark matter. It's actually more the other way around. If you have more dark matter, you will attract more normal matter, so they can form more stars. But there is also just some variation from galaxy to galaxy. Yes, it's not exactly the same.
I have maybe two questions. First, is that the space in between the galaxies, do we have any idea of the dark matter profile in between the galaxies as well? So instead of just a halo around each galaxy, what kind of density of dark matter are we looking at in between?
So the question is, what do we know about the distribution of dark matter between galaxies? On large scales, we think matter in the universe, and also dark matter, has some kind of filamentary structure that we call the cosmic web. It's like a giant spider web. That's because galaxy or the dark matter starts to clump together somewhat, and instead of being a huge cloud, it starts to first form some kind of pancake and then some kind of wire. And these wires intersect, and at the intersections of these wires, where there's the most dark matter and the most gravity, is where most of the galaxies form. But these galaxies are then connected with these strands of dark matter.
Any other questions? Great. Well, thank you very much for us for an interesting talk. And now we have several of the answers. All right. So answers to the quiz. As last time, can you just mark them yourself, and then later we will find out who won. But there will be 2 winners here and 2 winners who are watching online. So in total, we will have 4 winners. So that's great. Okay. So the first game. How many planets are visible? The correct answer is 3. So if you got that, put a little tick or 1 point. And otherwise, none for you this time. Okay. Is there a planet? No. No, there isn't. And the planet here is on the upper right. All right. There is a planet. This is very quick to check. There is one planet. And I think this is the last one for this game. There is a planet. All right. All right, second game. So, why is dark matter called dark? Answer is B, it does not emit light. But actually, it doesn't interact with light at all, so it also doesn't absorb light or reflect light. So, nothing at all. What is it not made of? It's not made of A, gas and dust. So obviously the most popular explanation now is that it's made of elementary particles, but also it's still a possibility that dark matter is actually made of primordial black holes. That means it's a totally different thing than regular stellar mass black holes. Stellar mass black holes are created when stars die, basically. And this has been, it's proven that this cannot be the cause of dark matter effects. However, primordial dark matter, primordial black holes are something different. They are hypothetical things that have been created in the early universe from these slight matter over densities. So they can have any mass, not the stellar mass related things, but much, much smaller mass. And this is still a possibility for dark matter. And the final, the number D, is correct because there are also scientists who believe that dark matter doesn't actually exist, and these effects can be explained if we just find a better theory for gravity. So basically the gravity that we currently use is incorrect, and that's why we see these effects that we cannot explain. So that's also a possibility. Now, 3. If a galaxy only consisted of visible matter, then the stars would orbit slower in the outside than in the outskirts of the galaxy than inside. And if we add now dark matter, we find that orbits of the outer stars would speed up. I will have a little video for you to see, but basically this is exactly what we need to match the observations that we have of galactic radiation curves. So here, if galaxies only had visible regular matter as here, you you would see that the inner stars rotate faster and the outer stars would rotate slower. But this is not what we see in observations, and observations require that the stars actually don't slow down as you go further from the galactic center. And to have this effect, we need to have dark matter to speed up the outer stars. So this is exactly what the answer says, that if you add dark matter, your stars in the outskirts of the galaxy would speed up to the required level. So who coined the term dark matter? It's a bit tricky. And 5. What happened to the dark matter here? So dark matter, as Bas talked a lot about, dark matter at best interacts very weakly with itself and with other matter. So as these two clouds of dark matter collided, they basically went straight through each other and switched positions to wherever they all originally came from. So that's what we see. And this is actually one of the strongest arguments against any kind of modified gravity model, because they cannot easily explain this situation here. So the answer here is B. If dark matter did not exist, these effects would be, so this one would be weaker, just different, and stronger. I will explain. So if dark matter did not exist, the gravitational lensing from galaxies or clusters of galaxies would be weaker because there would be less mass in them, and therefore the light would be bent less. Cosmic microwave background would still have these fluctuations. The fluctuations would just look different, but the difference would be measurable. So we can still use these fluctuations to see whether there is dark matter or not. So they wouldn't blur them out and it wouldn't be unaffected either. If dark matter did not exist, the baryon acoustic oscillations would be more pronounced. Why is this? If you recall what I said earlier, these central parts originally were just dark matter clumps, and these spheres, these bubbles around it, were regular matter. Now what happens, that if radiation no longer pushes the normal matter out, the inner dark matter clumps actually start attracting the matter back in. So these things blur out a bit. So having dark matter basically has a blurring effect on these structures of spheres. Right, here the answer is 27%. So what makes this seasonal pattern? The reason for this is that in June Earth is actually moving fastest through the dark matter of the galaxy, and in December it's moving slowest. I will show you quickly a reason for this. So as the Sun and Earth system is moving through the galaxy, so imagine this to be the whole galaxy, and you have dark matter everywhere. So in June, Earth moves fastest because the Sun and the Earth move in the same direction. And then it passes through more of dark matter particles. And this exactly the opposite thing happens in December, where Earth is moving opposite to the Sun, which means that it's slightly going slower, and therefore it passes through fewer dark matter particles. And finally, if we had a grain of sand every star in the Milky Way, we would have a large sandbox.
My sandbox the size of a
Huge. And our final tiebreaker. Okay, before we find the winners in the house, I want to say that for online winners, we have an astronomer winner whose name is Sarah Lesting, and a non-astronomer winner whose name is Online Nebulas. So we will get you some presents, and we will contact you after, and we will get you presents later. And in-house, can you calculate all your points?
Yeah.
I'm gonna like see. Did anybody get more points than 10? Get more than 10? So what? Huh? Amy. 10, 10, 10. Okay, so more than 10. So we have 3. And so astronomer or non-astronomer?
Astronomer.
Non-astronomer?
I'm not a physicist, but I'm not
I don't know. I think, okay. This is difficult. What do we count? Non-astronomer, I think.
Non-astronomer.
Non-astronomer, okay. So I think we have our astronomer winner already here. Well, how many points did you get?
11.
11, okay. And how many points did you get?
I have 12.
Oh, okay. In that case, can we hear your answer for the tiebreaker?
We got 2,000.
130.
Okay, we have our winners. Okay. So our astronomer winner is a little present for you. Congratulations. And our non-astronomer slash light astronomer winner. Congratulations, everybody. And now I'm going to give for the final word for Wendy again, so don't head out yet. Great, thank you. I hope you all had fun with the quiz. So just before we end, we don't have the exact details for next month, and I think the chances are quite high that we might just be online again, but we hope that you can join us, and we will be back here in the Burcht as soon as we can. It's been very great to see you all in person, and we'll let you know the details for next month. It will happen on the 26th of October, so we'll let you know. In the meantime, do check out astronomyontap.org for more. There's many virtual events happening, so lots of astronomy to check out. The great thing about doing this in person is that I can give these, not break them, 2 wonderful glasses to our speakers. So if you would just come up, I can hand these over to you.
Cheers.
Oh, great, thank you very much. And the other thing to say is a very big thank you to all of our team. This wouldn't happen. And thanks also to the Burcht for hosting us. Great, so just be mindful when you leave, not to all leave at the same time, but thank you very much.